The next thing we want to talk about is, what if a distribution is not normal? What if we can't define the entire distribution by just these two parameters, the mean and the standard deviation? So we're doing this a lot. We have some sort of distribution, and we're assuming it's normal, and it has a center point and it has a standard deviation. And one of the ways that we interpret this is if we take the mean minus 1.645 standard deviations, we end up cutting the curve into 5% and 95%. So plus a negative 1.645 sigma. If we move the curve, if we move this far down the curve, we cut it in 5% and 95%. But what if the curve is not normally distributed? What if the curve has negative skew, for example? So let me see if I can draw negative skew. And the way negative skew works is it's a little fatter in the left part of the tail. It's a little thinner here. It's a little fatter here, and then it's a little thinner here. And it might look like I've just shifted the curve to the right, but I haven't. I've drawn a little fatter over here, all the way to the left. You can see that the curve is a little bit fatter. There's a little bit more area here. It's thinner here, and so we've saved a little. It's fatter again, and it's thinner again. And the area under the curve still sums to 1, so I haven't drawn it super well, but anything that's above the black line must equal the amount that's below the black line elsewhere. But the point is that if I only go out the mean minus 1.645 standard deviations, I have an area that's actually greater than 5%. And if that's the case, if the area of the curve is greater than 5%, then the 5% var number that I've calculated is too small in absolute value. I haven't actually gone far enough to cut the curve into 5% and 95%. I would need to go further. Now the opposite is going to be true if I have positive skew. If I have positive skew, I'm a little thinner here, a little fatter here, a little thinner here, and a little fatter here. And now I can see that a positive skew is actually going to make the left tail smaller. And we'll try to come up with a little better drawings than these in a minute. But now I've gone too far, and my 5% var number is actually too large in absolute value. The next thing we'll look at is kurtosis. And I want to look at first positive kurtosis. If I have positive kurtosis, then I'm going to be a little fatter here. I'm going to be a little thinner through here, and fatter through here. And just like before with negative skew, positive kurtosis means that if I only go the mean plus, whoops, can't see that, 1.645 standard deviations, I'm actually going to have a area of the curve that's to the left that's greater than 5%. Once again, I can see that this area is actually larger than 5%. And so again, if I have negative skew or positive kurtosis, then the 5% value at risk number that I calculate using my standard formula, well, the mean plus negative 1.645 sigma, this is going to be my 5% var number, is actually again going to be too small. I need to add something to this to go further to the left to cut this curve into actually 5%. So if a distribution is normal, then I can fully describe everything with the mean and the standard deviation. But if it's the case that the distribution is not normal and it has either a positive or negative skew or kurtosis, then this is going to affect, and for our purposes, the left tail and the left tail risk. So let's just think about the skew very quickly. The standard deviation is the deviations from the mean squared. The skew is effectively the deviations from the mean cubed. And so if I have a lot of stuff relative to normal, if I have more stuff relative to normal, that's going to be really far to the left, and I cube it, when I cube these large negative numbers, they stay negative. If I have fewer things that are to the right that are large positive, when I cube those stay positive. When I sum all these up, I end up, and remember these are sort of scaled by the standard deviation, with a lot more big negatives than big positives. The sum is a negative skew. And so if I compute the skew of a set of data and it turns out to have a negative skew, that means that there's more stuff way out to the left than there is way out to the right, relative to the normal distribution. And if it's the case that I have a lot of stuff that's way out to the right, relative to stuff that's way out to the left, remember again, I'm cubing these. And so when I cube these things are positive, stay positive, but things that are negative stay negative. I end up with a larger amount of positive relative to the negative, and I end up with a positive skew, and my left tail is smaller than if it were straight normal. The kurtosis is to the fourth power, and this really magnifies things that are far from the center, far from the mean. And so if I have a lot of stuff that's really far away from the mean relative to the normal distribution, when I take it to the fourth power, that adds a lot of weight to these things that are far away, and it shows that I actually have tails that are fatter than they would be if it were normal. And if I have a negative kurtosis, then I have things that are closer to the mean relative to far away from the mean, again relative to the normal, and so it's fatter in the middle and thinner in the tails. The takeaway from this is that if it's the case that, here's other drawings that are from the textbook, maybe these are better. Again, you can see that the gray line is the normal. If I have negative skew, the left tail is fatter, and if I have positive kurtosis, the left tail is fatter. And so there's more mass to the left if I have a negatively skewed data set or a positive kurtosis data set. So if the skew and the kurtosis are non-zero, then they affect tail risk. And remember, tail risk is associated with an unlikely event. Usually refers to an underestimating the probability of having a big loss. And so we're going to focus on the left tail relative to the normal distribution left tail, thinking about the number that we calculated using the 5% VAR with normal. If the left tail is larger, then we've underestimated the probability of a big loss. And if the left tail is smaller, then we're overestimating the probability of a big loss. And so remember that a negative skew means the left tail is larger, and a positive kurtosis means the left tail is larger. And so if a distribution of returns has a negative skew or a positive kurtosis, the left tail is larger, the 5% value, VAR, value at risk number that we calculated earlier, is too small. And so a $3.4 million loss in the example above, well, we haven't gone far enough to cut the curve into the 5% and 95%. So two ways to say this: there's actually a greater than 5% chance of a $3.4 million loss. Or if I really want to go to 5%, I have to go farther. It's larger than that. So what do we do if there is a negative skew or positive kurtosis and we know that our 5% VAR using the normal distribution is wrong? Well, we'll use a numerical method or a sample method. Sometimes this is called a historic method, and we'll do this at a later date.